Hello. We're live. Hey. 1 minute early today, but that's all right. Get this out of the way. You don't need to see my streaming software in action. And let's see, I was going to get in early today and try to play with the microphone again, see if I can get this a little louder. Let's see if I can do that. So I've upped the gain a bit there. Tell me if your audio is a bit louder than it was. I noticed that if you're listening on something without very good speakers, something kind of quiet, it can be a little bit hard to get to the volume that you need. So trying to see if I can crank it up a little bit. Is that any better at all? Or is that about the same? Any improvement? Well, we'll roll that for now. See if it's any better. Doesn't seem like there's any complaints anyway. If you've got headphones, it sounds much better. So if you're listening on your computer speakers, I'd say switch. And yeah, I'm one of the quieter channels on YouTube, but that's the problem with YouTube, isn't it? Nobody syncs that audio up. Everyone's just all over the place with their audio. All right, let's finish last time's slides first. So we're going to finish a little bit about the physical layer. We were on microwaves when we ended, I believe, or we had just finished. There we go. We had just finished RJ45, that portion. We had finished talking about the terminating cable for Cat5. Notice that Cat5 cable is a bunch of twisted wires. This allows Ethernet to be full duplex, which means it can send and receive data at the same time. Something to think about later. Your computer can send and receive at the same time. Okay, half duplex would be that your computer can only send or receive, so it would have to wait before it can speak until it's done receiving a message. So Ethernet is full duplex. And that means there's actually technically two physical channels. You've got one going up, one coming down, one coming to you, one coming out, to send and receive. We'll talk about the star topology a little more today, but it's actually not that important. The main takeaway is that in the modern Ethernet network, every device gets its own Ethernet cable. We don't share anymore. And so a lot of what modern textbooks, not modern textbooks, but networking textbooks will talk about is how Ethernet avoids collisions and all these other things. Not that big of a concern anymore because modern networks, every Ethernet device has its own cable and that ties back to a switch. So that's why we're skipping over a lot of Ethernet stuff related to collisions and such. In these older topologies, you can see bus and ring. A bunch of computers shared a single Ethernet cable. They all talked into the same Ethernet channel, and they had to avoid tucking into that cable at the same time so that it wouldn't get all garbled. Now, this is still the situation with Wi-Fi. Everybody talks into the same air, and so some of the stuff that we're going to talk about will pertain more to how Wi-Fi avoids collisions. Which brings us to Wi-Fi, the microwave, the powerful microwave. This is a microwave pictured here, beautiful whirlpool model, and that is what is used for your Wi-Fi internet. Why is all Wi-Fi internet on either 2.4 gigahertz or 5 gigahertz, or in the distant past and still today in very rare instances on the 900 band? That one's not used too much anymore. But why 2.4 and 5.8 gigahertz? Because those are the temperatures that cause not the temperatures. Those are the frequencies that cause water molecules to vibrate really fast, and thus getting warm, and thus making your food warm. And that is how a microwave works. It emits a bunch of these frequency signals, a lot of them, a lot more than your internet devices do. Don't worry, your internet's generally not cooking you. But the earliest kitchen microwaves leaked these frequency bands so badly that the FCC couldn't reasonably sell them to anybody, because who would pay for a band where everybody's leaky kitchen microwave ruined it? So they figured we'll just make these free for public use. This is definitely one of those arguments for making things free for public use being a giant driver of innovation, because if the FCC hadn't incidentally made these bands free because microwaves were leaky, we probably wouldn't have Wi-Fi today. It's the fact that those bands were free that drove innovation in Wi-Fi, cordless phones, Bluetooth, and all the other technologies that communicate wirelessly like this. Now, today, microwaves leak a lot less. If you stand next to your microwave with a wireless headset like this one, and this has a 2.4 gigahertz receiver, and you turn the microwave on, sometimes you can hear a couple cracks and pops, but you really don't get a lot of interference from your microwave anymore. My router sits 6 feet away from my microwave, and there are no problems. So they actually kind of fixed the problem that caused it in the first place. And now there's not that much interference. But now there are tons of wireless devices that use these bands to communicate. Wi-Fi has a very unfortunate official name. It's one of those things that's named with numbers. Everything that's named in numbers generally is a terrible name. So if you're going to be inventing something and you've decided it's time to name it, don't name your thing numbers. It's just named in honor of the IEEE standard that it follows, so that's why it happens to be numbers. Anyway, 802.11 is considered Wi-Fi, and then a letter follows it to tells you which generation of technology it is. The generations of Wi-Fi tech were 802.11b, then A, then G, then N, then AC, and AX. Yes, in that order. You could have thought they'd at least use A, B, C, D, E or something, but no. No, in IEEE language it goes B, A, G, N, A, C, A, X. It's a terrible naming system. B was the oldest that you can generally still find on routers today. Most routers support at least the last 3 generations of tech. And N was the first one that started using the 2.4 and 5 gigahertz bands together. So most routers you buy today have a 2.4 and a 5 gigahertz network. A lot of devices you buy will have only a 2.4 receiver or only a 5 receiver. Only a 2.4 is more common because it's quite a bit cheaper. So things like smart bulbs and smart switches are often 2.4 only. And then in AC, they finally got close to gigabit speeds on 5 gigahertz in good conditions if you are near the routers. So wireless speeds are catching up with the last generation of Ethernet tech. Now, AX is trying to get rebranded as Wi-Fi 6. So you'll notice it's the 6th one if you counted out those letters. Hopefully that branding kind of sticks. Unfortunately, it comes at a bad time with 5G coming out. People think that those two have something to do with one another. They don't. So Wi-Fi 6 is not the technology that follows 5G. They have nothing to do with each other. And it's kind of annoying that they share a similar name and number structure. It also has nothing to do with Cat 6 cable. So again, confusing. Don't name your stuff numbers. Or if you do, name it like versions. 1.6 would have been clearer. Wi-Fi, like other communications we talked about earlier, uses QAM. So let's imagine that you're sending out a signal, a wave. Waves come out as sinusoids. Hopefully you'll learn that in physics. You could use its amplitude to encode a 0 or a 1. A little bitty wave is a 0. A big wave is a 1. That's simple. Or you could use frequency. When the waves come close together, that's a 0. When they're far apart, that's a 1. So in that 2.4 gigahertz band, there's a wide range of frequencies you can use. Or you can use phase, how offset it is. And the magic of QAM combines all those things to pack even more data into a single waveform while also making it incomprehensible to the human eye. Right, so the bottom picture there, using all those texts at the same time, makes it very difficult for a human to parse, but a machine can still figure it out. So remember, there's a lot of multiplexing going on in Wi-Fi, and there are a lot of devices who are screaming into the air their Wi-Fi messages at the same time. You're also in an environment, especially in dense urban areas, where there's lots of Wi-Fi networks online at the same time, and they overlap each other, and they all use that same frequency band. So multiplexing is all over. The simplest kind is frequency multiplexing. There's, I think, something like 21 2.4 gigahertz channels. Your router will just scan the air and pick one that it finds that's not crowded so that no one else in your area is using. if you live in a really dense apartment, it's possible to run out because everybody has their own router. It's also why they tell you that you should put your router in a lower power mode if you see that your wireless network is reaching, let's say, the end of your driveway, because then you could be interfering with your neighbors. That's only true if you live in a dense area and it's possible to run out of networks. Bluetooth uses a really cool and novel strategy. It hops frequencies lots and lots of times a second, and the strategy there is basically, what are the odds that we're going to have a collision? Like more than 5 times a second. Probably low, so as long as we just keep hopping, if we get an occasional collision, we'll lose a few transmissions, no big deal. So it basically just operates by magical chance. Bluetooth is a very funny tech that way. It just hops as fast as possible and works by chance. And now we're going to get into the mighty frame. So I'm going to transition over to today's presentation, the link layer presentation. This is going to be the first layer that matters to you as a developer. All right, this one is going to come back a few times over the course of the semester, and it's important to understand how it works, okay? So when we talk about transmitting things between machines, we transmit them in some kind of unit. We don't just send a continuous stream of data. We send them in blocks, and the smallest possible block, the smallest possible message that you can send is called the frame. Sometimes people call it the Ethernet frame because it's driven primarily by Ethernet technology, but even if it's transmitted over Wi-Fi or it comes in through fiber or cable or DSL, because ultimately, remember, all the frames you send out into the wide world are going to travel over one of those physical mediums, we still call it a frame. And so let's look at some of the parts of a frame. Some of these are actually in the physical layer, while others are on the link layer. This is one of those areas where the waters are a bit muddled. So if we look at this frame, at the beginning we have here, I'm going to look at the bottom row primarily. At the beginning we have something called a preamble SFD. Then we have destination address, source address, a tag, a length, some other various things here. Then data, FCS, and then an interframe gap. So let's look at some of those things. Let's look at the preamble first. So the preamble is definitely on the physical layer. You will need an oscilloscope to see it. So I have a picture there of roughly what the preamble might look like if you had an oscilloscope and you were able to read the raw electrical voltages right off the wire and watch them go up and down and everything. The preamble is 8 bytes long. A byte is 8 bits. So 8 ones or zeros, and it goes 1 0 1 0 1 0 1 0 1 0 1 0 back and forth for 8 bytes until it ends in a 1 1. So notice on the very last byte there is a 1 1 instead of a 1 0. That's how the other network card knows that it's over. And this syncs up timing between network cards, between network devices. We're going to learn what a NIC is in a sec. But this syncs up timing between them, between two machines that are communicating. If their timing isn't synced up, then the rest of the frame will probably be trashed. Okay, so it's important that two devices that are talking to each other over any medium have their clock synced up, or definitely over Ethernet have to have their clock synced up. And a lot of people don't consider this to be part of the frame because it's actually on the physical layer. All right, it's something that the network cards do without you being able to observe. So it comes before the frame. That's why it's called the preamble. The other part you get that's still on the physical layer is the gap. So after a frame is completely over, there's a gap in the signal between the two devices where no one says anything. There's just electrical silence. There's no communication. This is for various physics and engineering reasons, and the gap time depends on the connection speed, and obviously it's one of those things where improving it gives you an advantage because the less time you have to say nothing, the more information you can transmit. So of course it's been one of those avenues of development. Just like shortening the preamble is one of those goals of development. The shorter you can make the preamble to sync up the clocks, the better you can transmit data because the less time you spend on that overhead. And the gap time depends on the connection speed. Traditionally, it was 96 bits worth of time. So however long it would take you to send 12 bytes, that would be how long you would send nothing. So remember, you're not sending zeros or ones, you're sending nothing. The wire is completely clear. Even when you're transmitting a zero, zero over Ethernet isn't no electricity. A zero is one type of signal, a one is another. They're usually two different levels of electrical signal, but they're both active signals. It's not nothing or something. So for 96 bits worth of time, you would send nothing. But newer and faster versions of Ethernet have gotten it down to 8, 5, or even just 1 bytes worth of time that you would say nothing, which obviously gives you a lot less overhead. And this is used again for engineering and physics reasons. You just get the wire to clear, allow the receiver to buffer what it just got, sync up timing with the information that it just got, other physical layer tasks that aren't really important for you to know. So if you want to think about it conceptually, the smallest unit of data that we can send, that Ethernet frame, you can think of it as the 1522 bytes up to 1522 bytes that fit between a preamble and a gap. So every Ethernet frame starts with that 10101010 preamble, ends with 11. Everything after 11 up to the gap is the Ethernet frame. Some people also omit the last 4 bytes of the frame. That's called the CRC, and we'll look at that later. So some people would say it's the up to 1518 bytes between the preamble and the CRC instead of between the preamble and the gap. And then of those 1518 remaining bytes, 18 are the Ethernet header. We'll talk more about what the header looks like later, but that leaves you 1500 bytes of payload, 1500 bytes where you can put traffic in an Ethernet frame, or you can put information. The rest of that was overhead, and it's lost. So you lost that 8 byte preamble, you lost 18 to the header, 4 to the CRC, and then however many, depending on the speed, you lost to the gap. Those are all overhead. So why isn't it longer than 1500 bytes of payload? If we've already incurred that overhead, why don't we send, say, 4000 bytes in the payload? It turns out that today we could. Some people are working on getting those larger, but it was already standardized, so the devices, the hardware itself expects no more than 1500. But back in the day, the chance that you would get a desync was higher the longer you went. If you transmitted, say, 10,000 bytes, the odds that they would, the time between the two network cards would desync became very high. And if it desynced, then the whole frame would be destroyed. So that was unfortunate. So this was kind of established as a happy medium, like many things in engineering. It's short enough to usually not desync 99.9% of the time. The timings line up, but it's long enough to give you a substantial payload and make that overhead less impactful. So what do we call the hardware? I already mentioned this before. What do we call the hardware that handles link layer functionality? That's what that NIC is, the network interface card. A lot of people call it NIC for short. So network interface card, NIC, or you can just say NIC, but most people understand what you mean if you say NIC. And at one point, the NIC, if you had a traditional desktop or something, would have been its own card. So you had to buy a like an Ethernet card that would slot into, it wasn't PCI then, but it was the equivalent port that you would have to put it in. But today, network interface cards are very, very small. You can fit one into like, I don't know, the end of a pen or something. They're very, very tiny. And so today they're integrated directly with the motherboard, and they're usually relatively cheap. And you know that they're relatively cheap because of how many different things there are out there in the world that are Wi-Fi enabled or internet enabled. It's everything from your toaster to your refrigerator. You can buy things that are able to connect to the internet that cost less than $2 a unit. So you know that that network interface card must be relatively inexpensive. Now, of course, they make good ones and bad ones. There are tons of different manufacturers. Companies like Realtek, Broadtek, Qualcomm, Broadcom, Atheros, Intel all make network interface cards. And if you're a desktop enthusiast, if you like high-end hardware, a lot of desktop enthusiasts will try to find the motherboard that has the latest and greatest NIC. I think this generation, it's probably the fancy Intel one. But typically speaking, most people don't care what NIC they have. And the NIC's duty is to receive traffic on your Ethernet port or on the Wi-Fi and pass it up to your operating system. And hopefully that process is so seamless that you don't even realize that it's happening. It just passes along and you're none the wiser. What services are guaranteed at the link layer? So what does the link layer provide for us? What functions does it give us? So when we're talking about the link layer, remember that we're talking about Ethernet frames being transmitted between different network interface cards, different NICs, and that might be happening over Wi-Fi, over microwave signals, or it might be happening over unshielded twisted pair cat cables, so those Ethernet cables we were talking about earlier. Well, how about on-time delivery? Is the information guaranteed to arrive within some certain time window? So when we transmit a frame, is it guaranteed to arrive within a particular time? No. No, it might never arrive. So you might send something into the channel, into the communication channel, whether that be the air for the microwave signal or into the wire for the Cat5, and it might never get there. That could happen. Is it connectionless, or do you require a connection? If I send a message to another machine, we're connected by a network cable, and I want to send a message to another machine that's on the cable with me, or another machine that's on the Wi-Fi with me, do we have to set up some kind of relationship first? No. No, I can just talk, and hopefully they can just listen, because at some point down, you need to be able to have a connectionless connection, and this is that point. The upper layers that we talk about later do establish some kind of relationship, do establish a connection, and they use it by bootstrapping through the link layer. The link layer is where they initiate that relationship, initiate that communication. So no, A simply talks into the communication channel when they get a chance. That means that sometimes the communication channel might be busy and they can't speak into it. How about reliable delivery? Is this a reliable service? That means, is there any guarantee that what you sent is what they get, right? That the bits that you send arrive at the destination in the same state you sent them. And yes, there is a little bit of that guarantee. Ethernet uses something called a cyclic redundancy check, abbreviated CRC, to see if a frame arrived without any corruption. So all of the bits that were transmitted arrived at the destination. The CRC is 4 bytes long, and it's at the end of the Ethernet frame. I'll show the picture again in a moment. And some people call it the frame check sequence instead, or the CRC checksum. If you really want to get technical, CRC is the algorithm, and then the output of it is the frame check sequence. But if you want to be that pedantic, it's kind of annoying. So if you call it the CRC, that's fine. Some people don't think that the CRC is part of the link layer or part of the frame. They consider it part of the physical layer. We'll see why in a second. And that means that the frame is only 1522 minus those 4 bytes, which brings it down to 1518 bytes, of which, again, 18 are the header. Okay, so why might some people call it the physical layer instead? We'll look at that in a minute, but think about why some people might say that falls under a physical layer job instead. So if data from A doesn't make it to B, or it fails that CRC check, which we'll talk about how it does that a little bit, but it's actually not that important. Just to assume that if it fails the check, then we know the packet arrived badly. It didn't arrive the way it was transmitted. So if the message simply doesn't make it, or it arrives badly, does A get some kind of notification? Does A know that their message didn't make it to B, that it failed to arrive? So no, A has no idea if the messages that it sends reaches B. That means that you could send a message, it could fail the redundancy check, the CRC, and in that case it would be completely discarded. There would be no message back to A saying that their message didn't arrive. Now, error rates on wired mediums on Ethernet are extremely low, and because they're so low, CRC doesn't make any attempt to correct errors. There are some algorithms we'll see on higher layers that attempt to error correct and actually save a package that's partly damaged, so you can sometimes salvage it. But because error rates are so low in Ethernet, there's no point. It just gets discarded. And that means that it has to be retransmitted at some point, assuming that it's actually something that's got to arrive. And that means A needs to be able to retransmit it without getting any information that it didn't arrive. So that's something that you'll have to see at the higher layers as well. Now, NICs are able to do these CRCs extremely quickly because they have dedicated hardware to accomplish these. So they do them near instantaneously. They both compute the CRC to append to the end of the frame and resolve a CRC that's coming in nearly instantaneously using dedicated hardware. So keep that in mind when I ask later, why doesn't this layer also use a CRC? Because your computer, once it reaches your operating system, once it reaches the rest of the system, doesn't have any dedicated hardware to do complicated math. And so your computer, the overhead of computing something like a CRC might be quite a bit higher. So let's just look at how it works, and this is a gross oversimplification of binary math and modulus math and all this kind of stuff that's not very interesting to me. So first, let's say the whole world agrees on a number, and we're going to call that number g. In binary, this is a long polynomial number that IEEE chose for the whole world. And then let's say at the end of our message, we have that CRC field, or FRC, or whatever you want to call it. And we're going to call that field R. It's so many bits long. Remember, it's 4 bytes. Let's say sender has a message that they want to send. That message is M. M is usually quite long, right, because you have a large payload. So what the sender is going to do is they're going to generate that CRC field, R, such that M with R appended on it, mod G, is equal to 0. And then the receiver gets the message and the CRC appended onto it and computes M with R appended to it, mod G. And if the result's not 0, then you simply discard the packet. So the hardware that the NIC has in order to perform this very quickly is hardware that very quickly computes modulus operations and checks if something is 0, and also figures out what it needs to append in order to make MR mod G equal to 0 for the sending part. So just picking some numbers, let's say that G, the number we've all agreed on, is 4. M, the message I want to send, is 5. So we need to append something to 5 such that it's evenly divisible by 4. So I'm going to pick 6. Because 56, again, not addition, I've appended it on the end. It makes more sense in binary. We don't usually do this in base 10. So MR, which is now 56, 56 divides into 4 evenly, so 56 mod 4 is 0. If the receiver gets my whole message, that is M plus R appended on it, they do 56 mod the number that we all know globally, 4. So I didn't have to transmit 4 because we've all already agreed on it beforehand. And since that evaluated to 0, they now know that they can extract my message, my 5. Okay, and then of course R is the redundancy check. It's not needed, so it gets discarded. And this is why the CRC is considered by many to be part of the physical layer, because that R part doesn't usually get passed to your operating system. In fact, I think it can't get passed to your operating system. It just gets discarded. And since that R gets discarded, it's really only the message, the rest of the frame, that's part of the link layer. The redundancy check is mostly considered to be part of the physical layer. Only the NIC deals with the redundancy check when it makes this computation. If you're interested in the actual formula, it's this big long thing here. I'm never going to ask you about it again, but if it's something that's amusing to you, go ahead and try to figure it out. So can we see the CRC in Wireshark? Would we be able to observe it if we inspected a packet in our operating system? No, we would not, because the NIC handles the CRC check with its dedicated hardware. It discards packets that fail the CRC completely, so we would never even see them hit the operating system. If the NIC finds a packet that failed CRC, it gets discarded before it even hits the operating system, which means Wireshark wouldn't be able to see it. If it passes the CRC, then we wouldn't be able to see that either, because that part is handled by the NIC. There's no point in passing that data along. That would be a waste of the bandwidth between the NIC and the computer, between the NIC and the operating system. And just to make sure you were paying attention, what other part of the Ethernet frame are we going to be unable to see in Wireshark? So in either chat, what other parts of the Ethernet frame are we going to be unable to see in Wireshark based on what we've learned so far? We can't see the CRC. What else can't we see in Wireshark? Someone answered the 18 bits of the Ethernet head. We will be able to see those 18 bytes. It's easy to get bit and byte confused. Remember, 8 bits in a byte. So 18 bytes. We will be able to see the Ethernet head. What was the thing before the header called? The thing that comes before the frame. Give you a hint. It has pre in it. The thing that comes before the actual frame starts coming in. The preamble, right? Someone answered in chat. Yes, it's the preamble we also can't see in Wireshark. You're going to need to grab an oscilloscope if you want to see the preamble. And some people also say that the preamble is 7 bytes and then the last byte is a delimiter. So sometimes you'll see it referred to as a 7-byte preamble with a 1-byte delimiter. All just semantics. It doesn't matter. It's those 8 bytes at the beginning that you can't see. Some people call it 7 plus a delimiter because the last one has a slightly different message. It has a 1-1 at the end instead of 1-0. Okay. So how do we address an individual NIC? How do we name every individual NIC? Obviously, if you have a bunch of different network devices on your network, they should all have their own individual name. They should all be called something. Should we call them Steve or Bob? Well, probably not. Individual NICs are addressed by what we call a MAC address. Notice I didn't provide what MAC stands for because it's never used. The non-abbreviated version of MAC I don't think is used by anyone. Everyone just calls it a MAC address. Some people call it a LAN address or a physical address as well. Most people will just call it a MAC. A MAC is the name of your network interface card. Now MACs are 6 bytes long, so if you do the math, that means that you have 2 to the 48th possible devices. 2 to the 48th is not that many. It's only a few million. All right, and the first 3 bytes of the MAC are assigned to the manufacturer. So IEEE maintains the MAC addresses, and they will sell you a 3-byte intro, the first 3 bytes, for a small fee. This is actually incredible that the entire world agreed to let IEEE do this and mostly complies without any issue, right? Whether a device is manufactured in the United States or China or anywhere else in the world, everybody is compliant with this. They get their 3 bytes from IEEE. They don't try to go gung-ho and just decide they're going to steal somebody else's first 3 bytes, right? That's incredible. So whether the country is communist or capitalist or anarchist, we all follow this rule. The fact that the entire globe cooperates in this way on device manufacturing is really amazing. We'll see this as a recurring theme, that the internet depends on global cooperation for some standard, usually with IEEE being the one that intermediates there. IEEE, by the way, is the International Society of Electrical Engineers or something like that. I don't remember what all the E's stand for. I only know that it's comically often referred to as engineers exploiting engineers by those of us who are not big fans of IEEE. So anyway, the first 3 bytes of the manufacturer ID, that leaves only 3 for you to address the individual devices. Okay, so if you bought, let's say, the manufacturer ID 1, 2, 3, 4, 5, 6, then you have that as your first 3 for all the devices that you make. So if you go to that link, you'll see a bunch of the different manufacturer IDs, and you'll see that companies that manufacture a lot of devices, like say Apple or Dell, they actually own a ton of different of those first 3-byte blocks. So Apple might own, say, like 50, because how many devices is 2 to the 24th? Well, it's on the order of a few million. It's not that many. And you're going to need quite a few more manufacturer IDs if you want to keep making millions of iPhones. How many iPhones does Apple sell around the world alone? Quite a few is the answer there. So MAC are typically presented in hex separated by colons. Let's do a quick review of hex real quick. First, a byte, remember, is 8 bits, so 8 zeros or ones. And that allows you to represent the numbers 0 through 255. So the rightmost digit is how many ones you have, then how many twos you have, how many fours you have, how many eights, how many 16s, how many 32s, how many 64s, and how many 128s. So if you do the math, that means that the last number that you can represent is 255. If all of those are 1, you have 1, 1, 1, 2, 1, 4, 1, 8, 1, 16, so forth. Then you have 255. But that takes 3 digits to write out in base 10, the number 255. It takes 8 digits to write it out in base 2, which is way too long, so that's totally out of the question. Imagine having to write out a MAC address like the one in the bottom of the example here in binary. That means that each of those fields would take 8 digits. That'd be really annoying. But even imagine it in 3-digit numbers. That too would be annoying. It would make it considerably longer. So what we do instead is we use hex. That gets it down to 2 digits. In hex, we use the numbers 0 through 9, plus A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And so the rightmost digit is how many singles do you have? How many ones do you have? So that can get you to count up to 15. And then the next digit, the next to the left, is how many 16s do you have? Which means you can have up to 15 16s plus 15 in a 2-digit hex number. That lets you cover 0 through 255 with just 2 digits, the numbers 00 through FF. So let's do a quick example here. What is 1 1 in hex? If I give you 1 1, what is the value of that in base 10? Regular numbers, what is 1 1? I'll just put that in chat whenever you figure it out. What is 1 1? So we've learned how NICs are addressed. Where is all the link layer functionality handled? What do we call a group of NICs that are connected together? So what do we call a whole arrangement of different network-enabled devices with their own NICs tied together? We call that a local area network, or a LAN. And this is one of those terms that's kind of ambiguous. And you know it's ambiguous because it's got that word local in there. What is local? If there are multiple buildings apart, let's say we work at a large company and we have several buildings tied together, some people would consider the whole network of that company to be a LAN. Each building might be a LAN. When we're talking about the link layer, we usually say that the LAN that a node belongs to ends at the first router that serves that node. So we're usually talking about a group of machines that share a router. The LAN ends at the router. Now routers are then in their own LAN, right? So those routers might be connected to yet another router. They could be daisy chained. In fact, that's how the whole internet works. Routers connected to routers. So you might have 10 devices connected to a router. They're all in one LAN. Then that router is connected to 3 other routers, and they all terminate at another router later. Those guys are also in a LAN. So technically, your computer is part of both of those LANs if you want to think about it. But try not to make it too complicated. Think that your LAN ends at your router. So in your house, all your network devices are on your LAN. You probably have one router for your home. It's very simple in that kind of environment. Once you get into the complicated corporate IT environment, it becomes more vague, but we're going to try not to get into that too much. Now, MAC addresses, the ones we just discussed, the ones that NICs are named by, are not used to communicate outside of your LAN. So that address is used only to talk to devices that are on the same LAN as you. Let's see how much lag. Yeah, we're good. So those addresses, the MAC addresses, are used only to talk to other devices on your local area network. Once the traffic gets to your router is probably going to pass it along to the modem, which is sometimes the same device. Sometimes the router and modem are sold as a combo unit. And then it's going to move by the physical layer for cable, DSL, fiber, whatever, from your router to the modem to the institution's network. Okay, so that last connection, the connection between your institution's router to your service provider, so let's say your home router or John Carroll's router to the institution service provider, that could also still be considered link layer as well. Let's go back to the frame for a second and look at that frame header. All right, so here the preamble and the gap are not pictured. The first thing that we see is the MAC header, okay, or the frame header, Ethernet frame header, goes by many names, but we usually call the start of any particular transmission the header. So the first 6 bytes of that frame are the MAC of the destination, so which NIC you're trying to send this frame to. And then the next 6 bytes are the MAC of the source, so your own. All right, so source is obviously very easy to compute, and it's going to be stamped on almost every message you send. We'll look at the next thing that's pictured down there, the ether type, a little later on. But now that we know about MACs, we know most of the header. It's just the destination and the source. What if you want to send a message to everybody on your LAN? That's where the broadcast MAC comes in. This is also useful when you have a message and you're not sure who the recipient is or what the MAC address of the recipient is. We'll touch on that in a second too. If you send a destination of all ones, so FF and hex, then that goes to all of the devices on your LAN. So if you're getting that message, a message addressed to FFFFF, that means it was intended for everybody on the LAN to see. So let's look at some messages that might get broadcast. Let's look at Address Resolution Protocol, or ARP, commonly known as ARP. So we haven't learned about IP addresses yet, and you can just put a pin in that for now. But all the network-enabled devices, all nodes, need to keep track of which IP address is associated with which MAC. And obviously, when you first join a network, you don't have any idea of which IP address is which MAC. You have no info. There's no sign-on sheet or anything. When you first join a network, you get nothing. And so for devices to realize this relationship, for them to maintain a list of who's got which IP, who's got which MAC, they generate what's called an ARP table. And they'll store a pair, an IP address and a MAC address in a table, along with an expiration time for when they're going to try to figure that out again. So you don't want to keep it forever because those do tend to change. Your IP address tends to change. Your MAC address, again, built into your device, manufactured along with your device, and generally does not change. We'll talk about some exceptions in cybersecurity in a bit, probably next time. But generally, your MAC address does not change because it's manufactured into your card. So if you want to send messages to an IP, but you don't have their MAC in your ARP table, so you don't know what their MAC is, then you would send a broadcast. Let's look at some examples of what an ARP table entry would look like first. So you would have a MAC address, is at, and then their IP address, and then a time where it might expire. And you might have a series of these kinds of entries in your table. So those are 2 different MAC addresses, 2 different IP addresses, and then each of them have an expiry time, maybe 5 or 8 hours after you first picked up that pairing. All right, so the basic ARP packet is sent as a broadcast to everybody. So it's sent to FFFFFF. That's because you don't know who has that IP. And the contents of the ARP message are the IP that you have in question. So you're asking who has 192.168.0.53. In this case, you don't know who has that, and you want to find out. So you say, who has this address? And you also include in that message your own IP and your own MAC. And everybody that's receiving this ARP packet, which is, again, everybody on your LAN because you've sent it as a broadcast, can now add you to their ARP table without having to make a new inquiry, because they received this. So they see your source and your IP, and they know that they can add you to their table right away. Now think about how this can be used nefariously. The machine that owns the IP in question, so whoever has 168.0.53 will respond, but they won't respond over broadcast. They'll respond just to you because they already know your MAC. You sent it in the original message, right? So there's no need for them to send it out as a broadcast. They'll send it out just to you, and they'll respond with their MAC, and now you'll both have each other in your ARP table. Notice they don't have to respond with their IP because you just asked for that. We'll see how a ARP looks like in the lab either Friday or Monday. We'll look over some ARP traffic from your network because every network out there has ARP traffic. Even your home network is going to have a ton of it. Did I skip a slide? Nope. All right, so a little bit more on ARP. Remember, again, that you are only talking on the link layer inside of your LAN. So ARP is a protocol that only happens inside of your LAN. This is because your router is actually the one that's responsible for assigning those local IP addresses. We'll talk about that when we talk more about IPs and routers and everything. But it also means that everything that you want to send that goes outside of your network, the destination on the link layer is going to be your router's MAC address, because that's where it's going before it goes out into the great wide world. So everything that's destined for the outside internet will be addressed to your router at the link layer. It'll be addressed to your router's MAC so that it can propagate out into the world. Now let's go back to the star topology. Okay, what is this called? These two pictures of what a star topology looks like. In a star topology, every machine gets connected to a central hub or a central switch or a router. And there's some discussion we could have over how Ethernet avoids collisions and everything, and that's all pretty much rendered moot by the fact that most networks use a star topology today, and they don't typically share a wire. So all those discussions are unimportant. The boosters and repeaters and hubs typically don't exist in modern internet, Ethernet. But let's talk about the difference between a hub and a switch and a router, because these all have different meanings in IT terms. A hub, which again typically not used anymore, gets an Ethernet frame and it receives it, boosts it up, so increases the strength of that signal and transmits it back into the wire. So it might receive it and then immediately transmit it out back into the medium. These are obsolete, but there are still devices like this for wireless internet that receive the signal, boost it, send it back out. A switch will receive a frame and pass it only to the destination. So switch is what allows us to have star topologies and true dedicated lines. A switch connects a number of different computers or network devices together, which allows it also to broadcast to all of them as needed. But in general, a switch allows you to send a frame to one specific machine without sending it to others. And a router is like a switch, but it operates on a layer further up. So we'll talk about routers more down the road. So the switch is really the champion of Ethernet and the link layer in general. Here's a picture of a simple switch. You'll notice it just has a bunch of ports on the front, and you can just plug your Ethernet jacks into them. That allows your computers to talk to one another as if they were talking one-on-one. So switches are interesting things because they have no MAC address of their own. They have no address of their own of any kind. Switches are kind of like deaf mutes on the network. They don't make any of their own chatter, and they don't listen for ARP or any other kind of protocol. All they do is forward traffic along. So all a switch maintains is a list of MAC addresses and then the physical actual port that leads to that MAC address. So in this picture here, the switch has 5 ports. So they would maintain a table of 5 MAC addresses and which port belongs to that particular MAC address. How does a switch forward a message to a MAC address that it doesn't know yet? So how does a switch learn who's located at each port, right? If the switch is invisible, if it doesn't make any chatter of its own, if it doesn't use ARP, how does the switch know who's on which port? All the switch does is snoop the messages that it gets So if it sees that somebody on port 1 sent a message and the sender field, that sender field in the header was AA, then it knows that AA is at that port, right? So think again how this could be used nefariously if you could connect to a switch without permission. So if a switch doesn't have a particular destination in its table, so let's say that switch or that device at interface X with sender AA was trying to send something to BB, and the switch doesn't know which port BB is at, then it'll just broadcast it to all of the ports except for the senders. All right, and if you are BB, then you accept it, and if you're not BB, then you just throw it away like other broadcasts. So switches are able to self-learn by snooping the traffic that passes through them. A very interesting mechanism. All right, that's going to be it for today. We'll have the link layer lab on ARP either Friday or Monday, and then we'll finish up the link layer discussion on Friday. There will be a new homework up today later. The homework for this week obviously due tonight. So thanks for tuning in. See you guys Friday.